Welcome to the Warren Lecture. I'd like to introduce our speaker, Dr. Yafeng Yin. He's from University of Michigan. He's a professor there in the Department of Civil and Environmental Engineering. He got his PhD from the University of Tokyo in 2002. His research interests include modeling, design, and optimization of transportation systems towards sustainability and economic efficiency. Besides being a professor, he's also won some awards, such as the Ryuichi Kitamura Award and the Sella de Fermos Best Paper Award from Transportation Research Board, or Transportation Research Board Conference. And he's also the editor-in-chief of the Transportation Research Part C journal on emerging technologies. So I'll turn it over to Dr. Yin.
Good. Thank you very much. Can you hear me okay? Okay. Thank you very much for the invitation, and then actually honored to do this talk. Thanks for your time, and thanks for coming to my talk today. So my plan today is to talk about the macroscopic modeling of rice-sourcing systems, which we will apply to derive policy insight for regulation, and also we're going to look at the property of the systems from the supply side. Okay, so I think for this audience, I don't really have to spend our time discussing what are the rice-sourcing services. So the services are provided by companies like Uber and Lyft. So the company provides apps that match driver with passengers, and driver are the private car owners who drive their own vehicles to provide for higher ride for profit. So in essence, ride-sourcing services are crowdsourced taxi services. Okay, so the apps are free to use, but normally the platform charge like 20% of the fare paid by the riders. And since Uber started the service in 2010, more precisely 2013, that's when they started the ride-sourcing services. Okay, so the services have enjoyed huge success, but also create many controversies, such as the unfair competition argued by the taxi drivers, the congestions created by the in-service vehicles. So anticipating ride-sourcing service is going to play a more important role in urban mobility systems. So we started a research program 5 years ago, which aimed to study the operations of the services, trying to understand their impact and implications, and try to develop policy to guide their deployment and develop strategy to improve their operations. Okay. So we focus on ride-sourcing services, but I hope that we can shed light on the operation and management of other shared mobility services, because they share a lot of things in common. So in our research, I work with my former students at the University of Florida, and also my current student at U of M. And also Professor Hai Yang from Hong Kong University of Science and Technology is one of the important collaborators. I also work with Dr. Yafeng Yin from Didi Chuxing. So for those of you who are not familiar with Didi, Didi is a Uber counterpart in China. So in terms of ridership, they're the largest ride-hailing company in the world. So working with Didi allow us to peer into their operations and to make sure that our research is of practical relevance. And also work with them, and we can have access to their data, and then we can actually do some empirical analysis. Okay, so our work are sponsored by National Science Foundation, and then Didi, and also our regional university transportation centers. So in our research program, we look at 3 players in the systems. We look at the platforms, the riders, and drivers. We actually try to investigate critical issues associated with each of them. For example, for the drivers, we conduct empirical study to study their behaviors. So when they work, how long they work, essentially labor supply, and where they search for customers, and how they make route choice when traveling from one zone to another zone. For the passenger, we also look at the behaviors. We study their, for example, how to make a choice between riding alone and sharing with somebody else. And also their value of waiting time, value of the matching time, pickup time, and value of the in-vehicle time. And also we estimate how to make choice between ride sourcing services and other type of services. Okay? Essentially, we want to estimate the demand functions for them. And for the platform, we try to improve, work with Didi, we try to improve their matching technology, their dispatching, pricing, and using the information sharing as a mechanism to control the systems, and contract design to attract different type of drivers, and then and incentive design to incentivize driver to work longer or to work where the platform wants them to work. Okay? But more importantly, we take a system approach. We try to model the interaction of those three players and construct mathematical model to try to predict the consequence of these interactions. So we try to formulate a model to understand why the system performs this way and how it performs, and then think about how we're going to improve the system performance. We also try to derive insight for policy regulation for the policy for regulation, and also the policy for addressing the congestionality imposed by those in-service vehicles. And also how we're going to deploy the services in coordination with public transportations. So that's our goal of system approach. But today, I'm going to focus on two specific things, okay? We're going to focus on the macroscopic modeling, and we're going to use the mathematical model to derive insight for regulations. And also, we're going to look at, from the supply side, and what's the supply curve for the ride sourcing systems, okay? So I picked these two topics because, for example, regulation is highly controversial. On one hand, you have taxi drivers and some of the interest groups, and also even some of the researchers demanding more government intervention. On the other hand, you have a large portion of the population think that government intervention actually slow down the innovation in this marketplace. In fact, if you compare the traditional taxi regulations, we actually have fewer regulations for ride sourcing systems. Okay? The traditional taxi market is heavily regulated in terms of price control and in terms of market entry. But there's no such regulation on ride sourcing services. Okay? We do not regulate how to do the pricing. We do not regulate how many people we allow them to register for the platform and work for the platform. But last August, New York became the first city that restrict the number of ride sourcing vehicles. So essentially, New York became the first city that regulate or do the market entry control. So in this talk, I'm going to suggest that if regulation is necessary, we don't need to do price regulation. We don't need to do quantity regulation. We just need to regulate the commission they charge. I'm going to suggest that capping commission will be an efficient or effective policy if regulation is necessary. Okay? So we derive this insight from a macroscopic modeling of the structure and competition of ride sourcing market. So that's the reason why my plan for today is to introduce you this macroscopic model and to walk you through the process how we actually derive that insight. Okay? So in formulating this macroscopic model, we start from a highly simplified scenarios where we're going to consider a spatial homogeneous market, and we first construct a very aggregate model. Okay? So in building this model, we're going to look at ride sourcing market as a two-sided market with passenger on one side and drivers on the other side. So what platform does are two things. They determine pricing to bring the passenger and driver to the platform, and then use match to match them. Okay? So we're going to study matching, we're going to study pricing. And matching is very important because matching determines waiting time, which essentially we call market frictions. So market friction actually arrives in two stages, online matching and physical matching. So when the passenger sends a request to the platform, and the passenger has to wait a certain amount of time for the request to be matched with the driver, and then there's with additional time for the driver to show up. So passenger experience matching time and pickup time. So by symmetry, the driver also experience the same amount of pickup time, sometimes we call deadheading time, and driver also experience matching time. Okay? So we're going to look at matching technology to determine those time, waiting time. So because we try to construct a macroscopic model, we're going to view production, we're going to view matching as the productions. We're going to use production technology, production functions, to describe how efficient this matching process is. Okay? So the input to the production will be number of the waiting customers, number of waiting driver, and number of waiting customers. The output of the production will be a unit of time, how many match has been made. Okay, that's going to be the output. So if the matching is very efficient with the same inputs, the output can be higher. Okay, so now you're going to consider steady state. If you look at the passenger side, you have newly arrival of passengers, you have the matching rate, you have number of passengers in waiting. So at a steady state, you have a arrival, you have a departure. So at a steady state, arrival rate equal to departure rate, then the number of waiting customers equal to the average waiting time times the demand. So this is application of Little's law. So you have the passenger side, and then you can do the same thing on the driver side. So on the driver side, you also have the arrival rate equal to the departure rate, and you also can apply the Little's law to estimate the waiting time for the drivers. So therefore, if you plug in those equations into the production functions, and the production function essentially define a waiting online matching time functions. Okay? So the production function essentially define, relate the customer's matching time with driver's matching time, and also demand. So we know that there exists such a functions. Empirically, we actually can estimate these functions. So using Didi's data in Chengdu, we actually estimate these matching time functions. And this is the customer's matching time is a function of the demand and also function of the driver's matching time. Okay? So that's how we actually estimate the matching time. For the pickup time mathematically we can prove that pickup time is inversely proportional to the number of idle drivers. If you have more idle driver, the pickup time can be smaller. Okay? So if the idle drivers are distributed spatially in a uniform way, and alpha will be 0.5. You can prove that theoretically. But here we use empirical data once again from Chengdu, and we can estimate this is in Chengdu in that particular market, and what's the relationship between the pickup time and also the number of idle drivers. So alpha here is 0.56. Okay? So this is essentially the summary of the market friction, how we model the waiting time. Customer's waiting time equal to the online matching time plus pickup time. Driver's waiting time equal to the online matching time plus pickup time. And so the driver's matching time has certain relationship with the customer's waiting time, online matching time, and also demand. And then the pickup time is inversely proportional to the number of idle driver, which equal to driver's online matching time times demand. Okay? So we have such a system to describe all the waiting times. So in the discussions, and to simplify my notations, I'm going to simply use customers match this particular equations to represent the whole systems. So this equation essentially is a function between, represent the relationship between the customer's waiting time is a function of the demand and also driver's waiting time. Okay? So we can model, this is how we model the waiting time. So with this from matching and for the demand, okay? So for demand, we're going to assume that the demand for ride-sourcing services is a function of the fare, waiting time, and in-vehicle time. For in-vehicle time, we're going to assume to be given. And for the supply side, and given the number of drivers, and if you look at a steady state, if you look at the driver status, they're either occupied or unoccupied. So the number of occupied driver will be equal to the demand times how much time each passenger can occupy the vehicles. This is another application of Little's law. Okay? And also, same is the thing. The occupied vehicle, unoccupied vehicle will be the demand times the average waiting time of the drivers. So that's how we construct the basic modeling systems. Okay, so it's very simple systems, and you have 5 unknowns, 3 equations conceptually. So if the fair and free side is given, I can solve this system to estimate realized demand, customers' waiting time, drivers' waiting time. I can further decompose into the matching time and pickup time. So I can even estimate the social welfare this system is bringing to the society. Okay? But if you treat the fair and free side as decision variables, and this system essentially defines three implicit functions. And essentially, the demand is a function of fair and free size, and customers' waiting time, drivers' waiting time is the function of fair and free size. With these three implicit functions, I'm ready to model the market. Okay? So for the market, if I assume that monopoly situation, that's essentially Didi's position in China. So they're in a monopoly situation. So the monopolist is going to decide the fare and commissions to maximize their profit. And so the free side will be given by this equation. So this equation simply suggests that the labor supply market is competitive, and driver will keep signing up until the revenue equal to the operational cost and also the operation cost of the vehicle and opportunity cost of the driver's time. Okay? So you can solve this problem to get the formula, the pricing formula by the monopolist. You can also compute the social welfare, and then you compare with the second best situation where government or the society control the fare and free commission and free size to maximize the social welfare while ensuring certain profit margin for the platform and for the drivers. Okay? So the reason why we look at second best, because if you look at first best, because the matching technology is increasing return to scale. So therefore, if you try to achieve first best, and the profit will be negative. So it's not sustainable. So that's the reason why we look at second best. We want to ensure certain profit margin for the platform and for the drivers. Okay? So once you solve the second best, you can get the pricing formula, and you can also get the social welfare. You compare monopoly with second best. There's definitely a gap between them. So now the question you're going to answer will be, what type of policy we should impose such that the regulated monopolists become second best? So that's going to be the regulation policy you try to derive. Okay? You look for a policy, you impose that policy, but you want to regulate monopoly, achieve the second best. So we have done that exercise, and what we report in this paper is that, first of all, if you look at social welfare impact, although the platform does not own any vehicle, they behave exactly the same as a traditional cab company that determine price and free side to maximize their profit. So therefore, following the same logic, you want to regulate traditional cab company. If right sourcing company has market power, you also need to regulate right sourcing company. But different from traditional the taxi regulation, you regulate price, you regulate quantity, and here we prove that you don't have to do that. You just regulate commission. So regulating commission alone can achieve second best. The intuition behind this is, if you regulate commissions, so pretty much how much the platform get by finishing one transaction is fixed. So therefore, it's in the best interest of the platform to maximize the number of transactions. So essentially, that maximizing consumer surplus. So that's why this regulation can work, the intuition behind that. Okay? We also look at, in this paper, we look at the situation in the US where you have a duopoly. Uber is competing with Lyft. So in the duopoly situations, we show that competition between platforms does not necessarily improve social welfare and reduce price because the increase in return feature of the matching technology. So that's the reason, and we also show that regulating commission can improve social welfare. So that's how we derive the insight from this simple aggregate modeling framework. In this aggregate modeling framework, we do not consider any spatial and temporal heterogeneity. Everything is homogeneous. So, but if we want to evaluate the impact or the effectiveness of this policy, we have to extend the model. We have to consider spatial and temporal heterogeneity in the modeling framework. So that's the reason why we also extend the model along the time and spatial dimensions. Okay? So for spatial extensions, now we have to consider a spatially anisotropic market, so spatially inhomogeneous, and then we divide the whole city into different zones. So Didi and Uber, all those companies, they divide the whole city into different hexagons. And in each hexagon, you assume they're homogeneous. Okay? So then for each hexagon, and we assume that you have a demand functions. Okay? So you have a demand function describing the demand generated from these zones. And then for the spatial extension, given the total labor supply, we want to estimate how those total labor supply will be distributed spatially. So given n, we want to determine n sub I. Okay? So that's the purpose of the spatial extensions. And so we do that. We assume that the driver actually has perfect information, because the platform do provide this type of heat map to the drivers. So the driver actually know where the passengers are. So they have a real-time information about where the demand is. And then, so we're going to assume that driver actually has a perfect information, perfectly rational, and they go to the zone where they perceive to be the most profitable to compete. So at steady state, each zone will be equally profitable. Okay. So anyway, we're gonna here. So for spatial extension, given the total labor supply, we're gonna estimate how those labor supply will be distributed spatially. So we assume that every driver has the perfect information, and they go to the zone which they perceive to be the most profitable to compete. As a consequence, at steady state, and each zone will be equally profitable. Mathematically, and the numerator is how much the driver get from finishing one transaction. So either here is that, for example, 20%, driver get 80% of the fare, and the denominator is how much the driver had to spend on finishing one transaction. So how long they have to wait for get one order, and how much they have to spend on delivering the passenger to the final destinations. So the ratio determines a wage rate. That wage rate has to be the same across different zones. Okay, so that's how we actually determine the spatial distribution of the labor supply. So once you have this, and then you can actually once again formulate a monopoly problem, and the monopolist decide fare and fleet size to maximize the revenue, and then you have the demand function for each zones, the waiting time function for each zones coming from modeling the matching technology, and you have a demand, you have a vehicle status conservation constraints. This is how the total labor supply will be distributed spatially, and this is how the total labor supply will be determined. Okay, once again, you solve this problem, and you get a pricing formula, and then you can look at second best situation in spatial extensions. Okay, so that's how you can follow the same process of asking the questions. What type of policy you can impose such that regulated monopoly becomes second best. Okay, that's how you derive the policy insight when you have a spatial heterogeneity. So spatial extension is concerned about how the total labor supply will be distributed spatially. And for the temporal extensions, and you have to concern about how the total labor supply will be distributed across different time of day. Okay, for that, we can assume that driver actually will. We have to consider the driver's work scheduling behavior, because drivers do have a flexibility in deciding their work schedule, and they can decide when to work and how long to work. We're going to assume that this decision will depend on market situations. So to verify that assumptions, we can actually use data to empirically look at how they actually do that. Okay? So if, for example, if you look at one specific issues, so driver decide every day they decide how long to work. So does hourly income affect that decision or not? If the hourly income is higher, do driver work longer or shorter? So you can, to answer this question, you can do a simple regression analysis. You can regress the working hours with respect to the hourly income and also other socioeconomic attributes. And you look at the sign of those coefficients. If the sign is positive, which means that if the hourly income is higher, driver work longer. So this is sort of neoclassical assumptions. But sometimes you get the negative, meaning that if the hourly income is higher and driver work less. So this is so-called income targeting hypothesis. And drivers start a day with the income target in mind. If the hourly income is higher, it take less amount of time for them to reach that target. After reaching the target, the willingness to work diminish, and then they quit. Okay? So we use the Didi's data in Beijing, and we do this regression analysis. And it turned out to be 5% of them are income targeting, and 57% of them actually are neoclassical. But the key point here is more than 60% of driver, we adjust the work schedule in response to market situations. Okay? They do this, they do consider market situation and adjust the work scheduling accordingly. So that's the reason why in the temporal extension, we have to consider drivers' work scheduling behaviors. So to do that, we actually construct the time expanded network, and we divided the whole day into, for example, 24 intervals. So the node represents the starting the hours, and then this solid line represents the work link, and the dashed line represents driver are taking rest. Origin essentially the start of the shift, and destination will be end of the shift. Okay, you have end driver deciding work schedule. Essentially, in this network representation, is end driver choosing a path, because each path going to represent a work schedule. Okay, so this essentially this driver decided to work at 1 o'clock for 1 hour and take a rest for 2 hours and go back to work for 20 hours, then go home. So not realistic, but feasible. So the path flow will be indicating that how many drivers choose this work schedule. Okay, so once you know the path flow and you know the link flow essentially the summation of the flow of the path that utilize this link. The link flow essentially the hourly labor supply. How many drivers are working in this hour? So if you know the hourly labor supply, using our spatial model previously, you can estimate the hourly income. So the previous model, spatial model, essentially define a link revenue functions. Essentially tell you I know how many people working in this hour, I can estimate how much money, the hourly income. So once I have this, for a certain work schedule, if I summing over the income along the working links, so I know the revenue for this work schedule. I know the revenue, I can estimate the cost, because there's operation costs that driver have to pay. There are also some disutility associated with working early in the morning or working long hours. So I can specify utility function for each work schedules, and I can represent either income targeting or neoclassical behaviors. So once I do that, no matter how I specify utility function, I can assume that driver actually are trying to maximize their utility. So then at a steady state or equilibrium, and each chosen schedule will offer the same level of the utility, which is higher than or equal to any unused chosen schedule. So if you're familiar with transition network equilibrium analysis, this essentially I convert the market equilibrium into a network equilibrium analysis. And I can formulate variation inequality to describe the whole market situations. And then once I have that, I can formulate the pricing behaviors as a mathematical program with equilibrium constraints. So this is pretty straightforward if you're familiar with that particular literature. So once we have these two models, then we can go through the process to investigate how efficient that regulation policy is. Okay? So this is what we show in these two papers, and we actually show that even you consider this type of time-varying spatially anisotropic markets, capping commission remain effective. So capping commissions improve efficiency, market efficiency. Okay? So instead of elaborating on those two extensions, I want to share with you an empirical analysis, which we did using the data from Hangzhou, China. And Didi provided us the data, and they divide the whole city into 65 zones. And then the data involved like 8 million requests from the first 3 weeks of 2016. And those requests involve more than 30,000 drivers whose average working hour is 2.7. And then with the data they provided, we estimate the log linear demand function for each zones. And then we also For that particular city, and Didi implemented time-based pricing. So depending on the in-vehicle time, they multiply by a unit price to determine the final price. So during search pricing, and Didi going to determine a search multiplier and to determine how much they really charge for each zone. Okay? So in this empirical study, we only look at spatial pricing. We didn't capture the temporal pricing component. So we solved that spatial model to estimate how much price, the price that Didi going to implement on those in this city, in each of the 65 zones. Okay? So first of all, the price does vary from zone to zones. And from our model, we can decompose the price into 3 components. And the first one is to cover the operation cost. The second one is so-called matching externality. The third one is monopolist markup. Okay? So the 2 key points I want to highlight. The first one is the matching externality actually is negative. Matching externality is if you add one more customer to the platform, what's the impact to the customer's waiting time? So it's negative, meaning that adding one more customer to the platforms will reduce customers' waiting time. So this is because the nature of the two-sided market. Adding one more customers to the platform will attract more drivers to the platform, which reduce the customer's waiting time because the matching technology is increasing return to scale. The second key point is if you look at the portion of the monopoly markup, which is huge, okay? So this can justify regulation in that particular market. So our analysis can also estimate the social welfare and consumer surplus, producer surplus. But I will skip this part, and we're going to focus on regulations, okay? Because apparently, Didi has some market power in that market, and so regulation may be necessary. So once again, we're going to cap the commissions. So the commission cap in this case, because the basic pricing structure is time-based, so therefore the commission also will be time-based. Depending on the in-vehicle time, you just cap how much the platform can get from each unit of in-vehicle time. So we show that for this particular market, and if you cap the commissions and you can actually achieve the second best, you can improve the social welfare by 20%. But at the second best, and the portion that the platform get, the profit margin is pretty thin. So therefore, the proper choice of commission cap will seek the balance between the profit margin of the platform and also improve the market efficiency. But the key point here is we show that empirically capping commission remain effective. Okay, it's pretty effective policy. So major takeaway from my first part of the talk is we actually developed a Macroscope modeling framework to model the market and to derive the policy insight for regulations. And we show that capping commission has potential to enhance market efficiency. But the policy also has a different level of granularity. And you can impose the cap per trip, per unit time, per unit distance. And the cap can vary with respect to location and even time of day. So the higher level of granularity you go with, and it's more difficult to implement, but it's more effective. So you're going to make a trade-off between the implementation complexity and the effectiveness. Okay? So lastly, before I finish this part, I have to emphasize that I'm not advocating that we need to regulate Uber or Lyft at this moment because there are many good reasons not to regulate them. Okay? For example, the regulatory agency tend to be captured by the industry they're regulating. And even for the traditional taxi industry, a lot of economists actually argue that we should deregulate the taxi industry. And so a lot of arguments actually are applicable to here. So what I'm saying is judging the need of the effectiveness of regulation is an empirical matter. If a ride-sourcing company does have the market power in certain market, then that can justify regulation. So here regulation, and we suggest that if you really want to do regulation, you can simply cap the commissions. Okay? So that's the point. But I tend to believe for many cities, we don't have to regulate Uber or Lyft. But no matter what we do, we should allow traditional taxi company compete with Uber and Lyft on equal footing. So because essentially they provide the same service and they're substitute to each other. Okay? So I know this topic is going to generate a lot of discussion, but I'm going to stop right here because I have the other topic I would like to share with you, which I feel interesting. So this is about, we look at from the supply side only. Okay? So I'm going to look at right sourcing system as the input-output systems, like traffic network systems. Okay? So the system, you have rider flowing into the system, spending some time in it, and then flowing out. So for this type of systems, if you think about the throughput is how many passengers get delivered to the final destination per unit of time. Okay, that's the throughput. Accumulation will be the number of the passengers in the systems. I'm going to show you that the throughput of the system can decline with accumulations. I'm going to explain why this happened, how we prevent it from happening. Okay? So not every system is like this. For a regular input-output system like queuing systems, and you have such a phenomenon, if you plot the throughput accumulation versus throughput, you have such a relationship. So throughput increase initially with accumulations, and then once reaching the capacity, and throughput is going to remain at the capacity. So we call this a type 1 systems. Okay? A lot of input-output systems are like this. There are also the other type of system I call type 2 system, which you have this type of shape. There exists a critical accumulations. Before reaching critical accumulations, throughput increase with accumulations. And after reaching the capacity, and after reaching the critical accumulations, the throughput is going to drop. So apparently, on the left panel, you have efficient regimes, system operate efficiently, and right panel, the system operate inefficiently. And this is the highest throughput define the capacity. This we call type 2 systems. A typical example of type 2 system is a traffic network system, right? So we know the macroscopic fundamental diagram of the traffic network. And so if you look at the throughput of the traffic network, and there exists a critical accumulations, and then after reaching the capacity, when congestion arises, you have a capacity drop. So that's the reason why you want to prevent the congestion from happening, because after the congestion happens, and throughput of the system actually drop. So we're going to look at, the question we ask is whether the right sourcing system is type 1 system or not, or type 2 systems. So since we work with the Didi and we can have access to the data, and we can simply plot accumulation versus throughput to get this type of plot. But it turned out to be the data we have is pretty difficult to plot this type of curve, and we plot essentially the same curve from different perspective. We look at the supply curve. Okay, we look at supply curve. The supply curve will be if from this fundamental diagram, and so you can estimate speed. If you know the speed, you can estimate travel time. So the corresponding to this curve, the corresponding supply curve will be like this. You have a initially throughput increase. You have this is travel time, this is throughput, and you have increasing, and then you have a backward bending curve. Okay? So once again, the lower portion will be efficient region, the upper portion will be inefficient regions, and then the maximum throughput define the capacity. Okay? We call this supply curve. This is supply curve for urban traffic network. So now, what's the supply curve for the right sourcing systems? This is the left panel will be Uber system in New York City, and right panel is Didi's system in Chengdu. And each curve is corresponding to a level of labor supply, because not all the drivers are working all the time. So the first curve will be 10% drivers are working on average, like 30%, 50%, 70%, and 90% drivers are working. So it's actually corresponding to you have 1-lane freeway, 2-lane freeway, 3-lane freeway, and for each level of supply, you have one corresponding supply curve. And you can see that the supply curve actually are backward bending, and particularly for Chengdu, and this is in rush hour, and you have a backward bending supply curve, which means that the throughput actually drop with accumulations. So the system does operate inefficiently. So why this can happen? Why the right-sourcing system is not a type 1 but type 2 systems? Okay? So this is actually due to how they do the matching. And theoretically, we can prove that. At least we can identify there's two reasons why this happened. The first reason is called as white goose chase. The second reason is called as countryside delivery. Okay? So the first reason is because whenever a passenger sends a request to the platform wants to provide a match as soon as possible. They want to lock this passenger. They provide a match as soon as possible. So if they do that, when the system is experiencing supply shortage, when the number of idle drivers is small, and they have to match the passenger with the driver far, far away, the driver has to spend a lot of time on the dead-heading trip, on the pickup journey. So this is a waste of system resource because system experiencing supply shortage, and you send the driver match the driver far, far away, the driver has to spend a lot of time on the dead-heading journey. So this becomes severe, and so that's the reason why inefficiency happens. So you have a backward bending supply curve. Okay? The remedy for this will be, intuitively, this happens because you have a very large matching process. If you reduce the matching process, matching radius, so if you reduce the matching radius, you should actually reduce the portion of the dead-heading trip, and you can maybe eliminate or at least mitigate the inefficiency. So that's the intuition we have, but how this is going to impact the supply curve, and we need to do some theoretical analysis about it. Okay? So the second reason is we call countryside delivery, because it doesn't matter where the passengers are going to, and the platform treat them equally, which is the right thing to do, but the consequence of doing that is if the passengers are going to, for example, countryside, a very isolated locations, but the system also experiencing supply shortage, and if you match driver with the driver deliver the passenger to the countryside, and then the driver has to spend additional time waiting for the next match. Okay? So that becomes severe when the system experiences supply shortage, and that's also waste of resource. That's why the inefficiency happens. So therefore, to mitigate this inefficiency, you have to do something like indiscriminate matching or discriminate matching. You have to treat the passenger differently. You have to cherry pick which passenger to serve if you really want to maximize throughput. Because if the passenger are going to countryside, you hold them longer and providing matching priority to the passenger going to popular spot. And this way you can increase the turnover ratio of the drivers to improve the throughput. But this certainly creates inequality among the passengers. Okay? So certainly how we're going to do the demand rationing, essentially the form of demand rationing, how we're going to do that, and then you have to propose some model, do some theoretical analysis about it. Okay? So in the interest of time, I will go over this very quickly. So to demonstrate the white goose chase, we look at a spatially homogeneous market. And now we use a new macroscopic modeling framework because now we have to dive into the matching process. We really want to estimate how those market frictions are generated. Okay? So we view the system as a one double-ended queue with passenger on one side and driver on the other side. When they meet, they will disappear. So this essentially is a birth and death process, and you can estimate the steady state probability, and then you can also estimate all the performance measures, including the queuing time and also pickup time, etc. And then you can look at how adjusting matching radius going to change those performance measures and how that's going to impact the supply curve. Okay? So with what we show in this paper, and we show that with finite matching radius, it doesn't matter how small that matching radius is, the supply curve is always backward bending. But a smaller matching radius leads to a weaker bend. So if we reduce the matching radius, the curve will shift like this. But if you really want to get rid of the inefficient regions, you have to adaptively adjust the matching radius. We theoretically prove that by doing that, you can actually get a monotonic increase in supply curve. But how exactly in operation we're going to do that is remain an open question. We just prove that you can do it We don't know how you can exactly do that in operation. But theoretically, you can actually get a monotonic increase in supply curve and getting rid of all the inefficiency. Okay, so for the indiscriminate matching, we need to consider spatial heterogeneity, and then for that, we actually once again we cut into different regions, and for each region you have a homogeneous market, and then you have you treat each region as a double-ended queue, but the queue are not independent because they are connected by the driver's movement. When driver deliver a passenger from one queue to another queue, the driver become a rival at the destination node. So those queuing systems are connected by the driver movements, and you have a queuing network. Okay? When you consider new driver coming in and driver leaving, and then you have an open network, otherwise you have a closed network. Okay? So with that consideration, you can further decompose. For each zone, you have a service node, which is double-ended queue. You also have a pickup node, and also you have an area transfer node to capture the travel time between zone to zone. So then you also can approximate the performance measures and the queue length, etc. And then you can decide how you're going to do discriminate matching, how you're going to cherry pick which passenger to serve to maximize throughput. But I want to emphasize that you create inequality among the passengers, and then you try to balance this too. Okay? And so if you really don't care about the equity issue among the passenger, you can actually get rid of the backward bending portions. But if you want to maintain a certain level of equity, and you still have to suffer some backward portions. So that's essentially the major takeaway from my second part. So we actually empirically we demonstrate that the throughput can decline with accumulation in right-sourcing systems. The reason are due to white goose chase and countryside delivery. And you can by adjusting matching radius, you can deal with white goose chase. By discriminating matching, by cherry picking which passenger to serve, you can actually get rid of the countryside delivery. Okay? So anyway, so major takeaway summary to my talk today. I presented two macroscopic modeling frameworks. The first one is more suited to the analysis of the interaction between supply and demand. The second one really can represent better the market friction, can capture better the spatial interdependency of the market. Okay, so with this, I finish my presentation. I thank you for your attention. Thank you. So I'd be happy to answer questions if you have any.
So if the market, the right sourcing market is like duopoly, they are competing, like Uber and Lyft, they are
Yes.
competing. I guess
Yes.
they have a motivation to lower the commission. Is that still as important to cap the commission in terms of maximizing the social welfare or second best?
Right. So okay, the duopoly situation, as I mentioned in one of my So we actually examined the duopoly situations, and Uber competing with Lyft because the nature of the two-sided market, because the nature of the matching technology, and then duopoly really, the competition does not reduce price. Okay, in terms of social welfare, the competition does not necessarily improve social welfare either. We demonstrate that mathematically, but recently, I think one economist actually verified that empirically using data from from New York City. If you think about Uber, in essence, this is not an isolated market. So even I'm in a monopoly situation, for example, Didi situation in China, they're still competing with taxi drivers, right? So they're still competing. It really depends on the demand function for right sourcing systems. So that's the reason why for certain market, they have market power, and for certain market they do not because there are so many competitors. So I'm in monopoly situation for right sourcing services, but not necessarily I'm the monopoly in the ride-hailing market, right? Yes?
In the second part of the presentation, the queuing or the countryside delivery reminds me of a different queuing discipline. For example, instead of having first in, first out, you can have shortest processing time. Did you consider this different queuing discipline in your model, or do you know if the companies are considering such thing?
That's good. That's a good question. So, in terms of matching, so if you think about, because the reason, okay, there's different, it's really based on competitions. Because Uber is competing with Lyft. So therefore, when they do the matching, so they know there's an efficiency, there's some efficiency in the systems. But they try to, because the competition, they try to lock up the passengers, right? So that's the reason why, for example, they want to provide a match as soon as possible. Because if I provide you a match, and you don't mind waiting for additional time for the driver to show up, but because I already provided a match, you already matched you with the driver, right? You do not switch to another platform. So that's sort of limited their choice of how they do the matching. But then if you think about Didi, they're in a monopoly situation. They don't really have competitions, and people only, when they do choose the right sourcing services, they only has one option, right? So then Didi in a situation that they can allow passenger to wait longer, and then they can do a system-wide matching. So they solve the bipattern matching problem, and then they can optimize some objective functions, right? So if they have this type of flexibility, and then they can decide, okay, how can I cherry pick the passenger, how I can serve them. So, but I don't think now they actually, so right now they're doing system-wide matching, bipattern matching, but they haven't done anything about, so in some way they actually do something, okay? They actually decide, depending on where the passenger is going to, and they do the matching differently. They are considering that.
My question is, I'm curious about that curve. So if the ride sourcing system is converted to a street hailing system, will the curve be different? Will there still be a backward slope?
That's a good question. So you talk about taxi.
Yeah.
Traditional taxi, street hailing, right?
Yeah.
So for street hailing, you don't have a backward bending. So for street hailing, you sort of, the supply curve will be similar to, okay. For traditional taxi services and street hailing, you have a curve similar like this. But of course, when the search friction of the street hailing will be larger than the waiting time, okay, the passenger's waiting time with street hailing going to be larger than e-hailing when the market is not dense. But when the market is dense, so street hailing actually leads to less waiting time for the passengers. Okay, so the curve is different. But the short answer to your question is monotonically increasing functions. And if you compare with our ideal case, and in this level, the waiting time is going to be larger. And in this level, the waiting time is going to be smaller. Because if you think about when the market is dense, you call a taxi from street. Actually, your waiting time is less than you do the e-hailing from the app. So you can prove that mathematically. Right. And empirically, we verify that. Okay. Right.
First, I have a question, because this is part of the system I don't understand. We're saying that is a customer-driver matching, but is there an actual bidding by drivers on the price offered?
No.
No. So
No.
basically, the platform decides what the price is,
Right.
and so the driver has no option
Right.
about it.
Right.
Okay. So in terms of the countryside delivery, which I like the term,
Right.
That was the argument of Minnesota taxi cabs
Right.
charging outrageous prices as compared to other urban areas, because they said, well, we're going to deliver in the countryside, we have to return back. Now, in the case of the taxi cab company, the cost is all borne by the company, because the cost of the cab to return to a dense client
Right.
location
Right.
is going to be paid by the company.
Right.
But in the case of ride sharing,
Right.
matching, it's borne by the driver.
Yes.
So the company has the incentive of increasing the price regardless of where the destination is. The only cost they're going to pay is that they're reducing the driver pool, but sending the driver to the countryside without compensating them for them coming back where the clients are, they don't care.
They care because if the system has sufficient labor supply, they don't care, because the system throughput will depend on, you have a supply, you have demand, it's a two-sided market, right? The system throughput is dictated by the shortage side. So if the system experiencing, if you have a demand larger than supply, and the system throughput will be dictated by the supply. And if you have a sufficient supply, and the system throughput will be dictated by the supply side, or the demand side. So therefore, they don't care if you have a sufficient labor supply. In the off-peak situation, they don't really care, because they can maximize, they have sufficient supply anyway, and as long as they can maximize the number of the passengers they serve, they maximize their revenue. But when your system experiencing supply shortage, okay, in peak hours, and also in many of the markets that right now ride-sourcing company has difficulty in recruiting drivers. So in that situation, the throughput will be dictated by the number of drivers. So that's the reason why you want to increase because you have a closed network, the number of drivers given in these situations. So if you reduce the number of drivers working for each transactions, you can increase the turnover ratio of the number of drivers, and you can actually maximize your throughput. And you can actually maximize the number of passengers you serve, you can maximize your revenue. So that's the reason why they care when the system is experiencing supply shortage. Right, thank you.
I know that in Didi Chuxing app, they have something when we go in a far distance, then they will become a taxi calling app for us. They call the traditional taxi instead of using the Didi service inside the app. So in this case, that even matter for that curve to be like inefficient anymore, because they can have the other supply from the traditional taxi inside. So when I using the Didi app, they have an
traditional taxi company, driver working in, okay.
Yeah, and then I think in the rush hour or when we have to go in the far distance, they actually did not provide us the Didi taxi, but they provide us like the traditional taxi instead. So in this case, will the model change? Or does it even matter to them anymore that they have to kind of make the system efficient because they can use the traditional taxi in replacement of Didi taxis?
Okay, but it doesn't matter. First of all, I think the most important issue about this supply curve is about the technology, right? Your production technology. So it's really the major key point is whether you do street hailing or e-hailing. So whether you call the vehicle at the side of the street, or you just call from the platform, right? So that matching technology decide your supply curve, the shape of your supply curve. And so the second, so I think you suggest that at the Didi platform, they actually had a traditional taxi driver working for them. They can actually get additional labor supply and to help the shortage situation, right? So this, which essentially, in that situation, you will mitigate, because remember the supply curve is corresponding to a level of labor supply. If you have a different labor supply, and you will have different, so this is, for example, 10%, 20, 30%, for 50%, 70%, 90% drivers, right? So corresponding to one level of labor supply, you have a supply curve. So what you're saying is if you can adaptively adjusting the level of the labor supply, and essentially you're connecting multiple curves. Okay, so depends on how you do that, adjust that adaptively, and then your supply curve will be different. Okay, but if the system experiencing supply shortage, and if you use the same matching technology, you still have that backward bending portion. So meaning that even I have additional labor pool, and if in a situation that the supply is larger than, the demand is larger than the supply, and if you do not change your matching technology, and you still suffer that inefficiency.
Yeah, so let's thank our speaker again.
Thank you very much.